Okay. So next stage. Imagine that you'd like to make the temperature corridor left. For example, 0.1 degree. What will happen?
On and off.
On and off, but with bigger frequency, isn't it? It is clear. So next stage, 001. Do you think your refrigerator how much, what will be the time your refrigerator will work before you will blow up your compressor? Some minutes, no more, no? So you will blow it up. It is clear or not? So that is why. Now imagine the rule of Big Bang control. You have two policemen which are putting on one side and from the other side the victim. No? Now what happens? You from one side, for sure, if your policemen are more strong than your victims, he will not go outside. It doesn't matter if he is strong or if it's not. It doesn't matter. What is matter is that he will be between them. And if the distance will be small, what happens? Or the policeman will tell me, for such a small salary, I have to work so hard, putting the guy in each step, or they will beat the victim so strong that after a small time they will kill him. So, what happens here? Two things. First, Big Bang ensuring you that you will not feel what? Perturbations. It is clear, no? Outside temperature, difference of temperature doesn't important, doesn't matter. From the other side, you will have clearly speaking disadvantage. What's the disadvantage? You should take care of the policeman, which means actuator, and you should work. You should do what? You should be also take care of the victim. You will kill him or not. So this means, or you will spoil the plant, or you will spoil what? Actuators. The both stories are bad. What is new here? The new bit of information, what? So I need to take care about two things. First of all, no one theory of control is good if it is not considered perturbations. Yes. If you don't know perturbation but know just their upper bound, what you will do? You will put the policemen so strong that you will not be able to go outside. Okay. So that is why what is important here. Important here are two things. First of all, you will not be able to pick yourself, to keep yourself inside of the zero peak when you will continue standard differential equation. Why? Because let's say, imagine that if you are working on standard differential equation, what happens? Linear system, let's say, non-linear linear system, whatever. You will never stop. Imagine that you have viscous friction. You will have asymptotical conversion. Imagine you will have a car will never stop, which will just approach. Is it good or not? It is bad model of the dry friction. Dry friction, what is it? Sine function, isn't it? So that's really strange because you see what happens. If I'm putting my stomach there inside, so what happens? The car will be more heavy, isn't it? Theoretically, it will change my equilibrium point, no? If we will do standard smooth contact. But it doesn't happen. Why? Because I'm able to ensure the convergence under uncertainty, under stack. So that is why two things important. First of all, we cannot derive the mathematics for discontinuous right-hand side. The standard mathematics should be changed. Why? Because all of the story we know about differential equation, what you're reading in the book of Halil, the right-hand side should be lifted, isn't it? So it means that you will be able to make derivative. Are you able to do it in band system? No. So that is why before to teach the course, I need to start with differential equations with discontinuous right. So unfortunately, the whole stages of seminar will be tomorrow. But this is the first part. First part, what we need to start to study equation with discontinuous fraction. So what does it mean? This means that we need to have new notation. Why? Because we need the function which is differentiable, because finally we will pick up the solution like solution of differential, but it will be still so function which needs to have derivative. From the other side, it is not a big deal. So why? Because your function cannot go to infinity. If it will go to infinity, you will kill yourself. So that is why there is a special notion. This special notion, it's not for such a screen. So my laser is not for a screen, so I will teach with a finger. So this is absolute continuity. Absolute continuity means that you need to define a function which has derivative, but when? Just practically everywhere. That's what we are telling. So it is just math definition. I will skip it. I would like, oh, I don't know what happens. Well, I can see all screen. So what happens here? I need to tell the function we'd like to differentiate. It is so-called absolutely continuous function because it could not be Lipschitz, but the derivative should be exist practically everywhere, because there are some points which it will be not exist. So let us.
Here is the pointer.
Okay. Standard function which is not differentiable but continuous. What is it? It's y equal to modulo of x, isn't it? Is it continuous? Yes. It is differentiable. From the right side you have 1. From the other side you have -1. Is it clear? So this function is Lipschitz. Okay, that's good. But the point is that there is a set of functions which is not even Lipschitz, but you can have an idea about the upper bound of the ability. So such a class of function has name absolute continuous function. And this is very simple. This is a function which can be represented as an integral. And integral should converge. So the only restriction is that this function will be measurable in the Lebesgue sense. If it is a bad word for here, let's say it's Riemann sense, it's enough. Okay? Is it too much? Say it. You will tell me. It's good. Please, because you see, you should stop me. So that's precisely an example of not too good function, but still, what? Still absolutely continuous. What is the way? Why it's a bad function? Because here at zero, it is not only not differentiable. The derivatives go where? To infinity. Why? Because the derivative of square root of x is 1 by square root. No? Is it clear or not? Clear? The derivative of square root gives you what? The x in different denominator. So you will go up to infinity in derivative, but not in the function. So the integral will converge. This is for sure not differentiable, but still good function. Why? Because you can found an integral. Is it good? So next stage. You've seen this in the first class of analysis, isn't it? So it is, you know that when x goes to 0, this function goes. So it is continuous function, yes? So now let's start to differentiate it. This story comes out, and what happened here? The argument of sine function is starting to oscillate like that. You cannot simulate it well because the frequency will go to it. So, but what happens? You will at zero, it is not different. It is not differentiable, but lateral derivatives do not exist because you don't know this number. And here you have another function. It looks similar, but what's the difference? The difference is that here you had x squared inside of x, so you will leave here 2x, isn't it? So, and that's what you have here. And then this story is also not a big deal because it is not differentiable for both sides. But this story is bounded, isn't it? This story goes to 0. So good, works. So this function is absolutely continuous, but this function not. That's the story. So the point is that continuous function should be not so good, can be not Lipschitz, but even absolutely continuous. That's a very important fact because when we will start the next stage, I mean super twisting algorithm, you will have such a term like a square root. And so that's important to understand. Here. Okay. So what is important here is the following. The properties. Okay. it is clear that if it will be integrable, the derivative of it will be integrable. This also both will be differentiable. All of these properties are standard -1, which maybe I will take in the course. The story is that if you will have composition of two absolutely continuous functions, one from the other, it can be not absolute. I will not put it here, but it is very important to know. So then we will go to the very difficult story from the viewpoint of normal logic, but it is very important. So what's the distance normally? The distance between 2 points. Distance is you are measuring distance from one to the other. And if you will measure the distance from B to A, it will be the same. Isn't it? It's not the same for more. Now we will study what? We will study sets. Why we will study sets? Because we need to understand what happens with the right-hand side of the equation, okay? And if you will have an uncertainty, what will happen? You should fight with the sets, not with the points, okay? And what is interesting is the following. How you are measuring the distance between point and the set. So what you are doing, you are searching the nearest point, no? Nearest point, isn't it?
Yes.
So what happens here? Here I would like to see the distance between two sets. What happens here? What happens here? It is really funny story because distance between two sets, when one is instead of the other one, inside of the other one, this story doesn't happen. So the distance to M1 from M1 to M2 is not as the distance from M2 to M1. Funny. For me, at least, it was funny. I should be really modest and tell that when I've seen it first time, I told guy, are you okay with your head? So what happens here? You see, if M2 is a big, if M1 is a small, and M2 is a big, for sure the distance from M1 to from M1 to M2 will be zero because you're inside. But the point is, if you will change, if you will see M2 to M1, you have to search for the farthest point. Farthest point is this. So what happens? You will have the distance which is more than this. And that's what I shocked first time. Because it's not trivial point, isn't it? So what happens here? What do we need is to give a new definition of the maps, because we will map what? We will map the points. No, we will map the sets, and we have to establish the distance from one set to another. So what does it mean? This means that if you are approaching from the small set to the big set, the distance will be zero because you will be every time inside, isn't it? Is it clear? From the other viewpoint, and it will call upper semi-continuous because you are going to the fourth set like this. And otherwise, if you will go from the bigger set to smaller, so what happens? The distance will be positive. So upper semi-continuous, it is a case when you are going from the smaller set to the wider. So why it is important? Imagine remember my image. What I was speaking about, I was speaking about strong policemen, and so they need every time to cover the force of victim. Okay? That is why, if you will consider perturbations, you have to speak about upper semi, because the strong policemen should be covered the victim. Okay? That's a key point also. So 2 bits of information. First bit of information. There are continuous functions. There are differentiable parameters. Okay? What is in between Lipschitz function? It is enough or not? It is not enough because there are some functions which are still not Lipschitz, so means that the derivative could go to infinity, but they can be presented in the form of integral. So that is why they can be a solution of differential equation. Okay? That's the story. That's first and bad part of the math. Unfortunately, it will be even worse one. But I'm trying not to bother you too much. Okay, so what I would like that you understand is the following. You see, this is a definition and this is an example. And this example is a key in the example. So when you are putting sine function, which is a symbol of what? Discontinuity, isn't it?
Yes.
So what you are doing, you are telling that it is not a function because I cannot tell nothing about its value 0. Why I cannot do it? Because if I will put 0 here, I will not stop the car. Why? Because never knows, is it me inside of the car or is it you, slim guy, which let's see, you don't know precisely why. So what happens? You need to find an equilibrium. So your control should be so strong that it should support any mass inside of the car, isn't it? So that is why if you will define sine function like this and this, doesn't work. You can never suppress perturbation. You can never compensate. So what you need to tell, okay, guys, I will have the same story, but at 0, I have to put what? That. It's a possible value between -1 and 1 will belong to my function if I would like to make it upper semi-continuous. Why? Because I will go, if I will go to this, on this side, I will reach bigger set, isn't it? From the left side, I also will reach bigger set. That's what I told here. I need to reach, if I'm reaching the bigger set, I am okay, I'm upper semi-continuous. Okay? So, Of course, it is not a function in standard way, because what is a function? The function, if I know just one value. Here, it is multi-valued function. Why? Because you need to tell that here you have a set. And that's the point. So this definition allows you to tell that if you will have perturbation in the system, you will have an opportunity to compensate. That's historical remark. First person which told how to deal with discontinuous equation was Professor Karate. But he was working only on P. And it is not important for us, because we are working normally in the feedback. We need to introduce X also. So then it was a second story by Polish school, which was completely killed during Second World War, and they was from Ukraine. Today they was from Poland, but at that time it was Ukraine, and it is Zaremba. And that the only person which had understood what to do was Professor Filipov. He made a very important presentation during the third IPA Congress in Moscow in 1960. International Federation of Automatic Control was founded by Soviet Union and the international community. And the first Congress was in Moscow, and all of the theory was developed by the persons which I built personally. Unfortunately, all of them are died. Professor Filipov invites me to his seminar, and why? And it was my first and most important publication. This book was a member of my PhD committee, and Professor Fridman was my scientific notes. They've made a first contribution to the topic. So, and then they talk about the differential equation and this continuous fraction outside, and they consider very simple case, which is very important for us. Very important for us, because you see, they suppose that we can divide the domain into subdomain, for which always is okay, and you can continue solution till the border. It is not too abstract, and then it was a key point mentioned by Filipov. Filipov told the following. Okay, there are three cases. Imagine that you have that's what you told, Professor. I don't know. I think this, Professor. That's what you told. Imagine that you have some sliding surface, and we have two options. One, to go through, and the other one, the situation with two policemen. So you should follow what policemen are telling. So imagine that you are living in your family. So what you are doing normally? You have some let's say compromise between two parts, no? Otherwise you will destroy the system. That's how discontinuous control system is well. Let's say in any family there is conflict of interest. So what you have to do to keep the family, you need to make a compromise to be every moment in conditional surface. If you will not do it, you will lose the track, isn't it? So, and that's what Professor Filipov told. Please make a convex closure of these vectors and follow the tangential surface. If you will be in tangential surface, you will never lose the track, isn't it? That's how it works. So that was a definition made by Filipov. If you have two surfaces, I mean two controls, so you have a vector with a field with four vectors. So you have to make a rectangular and choose a vector with just with one point inside. So and here precisely explanation what I've told already. Okay, imagine that you have this equation and you define sine of 0 is 0. What will happen with your perturbation? They will destroy the system. Yeah. Because it will be just one point. You cannot find a lot with a dragon which has infinite number of heads. Is it clear? So what does it mean? This means that you have to go into the set and tell, okay, I will define sine as any value between minus and 1 and plus 1, such as I will have this consensus. I will be in equilibrium. So if I should be in equilibrium and my perturbation will be less than 1, so what I will do? I will stay. Okay? That's a key point I would like to explain you. Maybe it was even stronger that you were waiting for me, but let's see. I asked before in advance, Professor Side, stop me if I'm to be too deep in math, and I'm sorry about that. So then regularization procedure. So let's see what happens with my father-in-law. He told, okay, Filippo is a clever guy, but then what I have to do? Very literally. What I need the value of control signal, isn't it? If I don't have a value of control signal, I'm not engineer. Is it correct? So he told, okay, imagine that I've told to engineers that they need to find convex closure of the cell. They told, goodbye. It is not, they will tell goodbye. It is not a good story. So why he was clever? He told, guys, what I do need is to have something simple like algebraic equation. So what happens if I would like to have an equilibrium here? If I would like to have an equilibrium, I should find such a control which nullifies this function, right hand side, because I would like to stay where? Equilibrium. So what should be a control? A control should be a value which allows me to stop at 0. So what I have to do, I have to differentiate right hand side and find unit. So what he told, if he told that to find it, I need to differentiate and to find the value of control which called equivalent control. So and that's all. So he told, okay, imagine that I have sine function in the right hand side, and what I should do? I should find the value of right hand side, and there are two methods. One by Filipov and the other one by Lupi. And what he told? Okay, Filipov told, I need to put this and I need to find the square. Okay? What Lukin told? Lukin told, I don't need to put the set. I only need to find what U. Okay, what I'm doing, I'm modifying the right hand side. So it is clear that if I'm modifying the right hand side, you can be not linear like here. Changing Q, I can have a curve. But what is my goal? Compromise to be every time where in tangential surface. Then I will differentiate the story and I will have the condition which looks like standard differentiation of Laplace function. I need to derive to make derivative x and define it for x dot, no? And multiply it for x dot. So is it clear? I'm differentiating x and s and then multiplying for x, isn't it? So what I'm doing, I'm having equation to be a tangential surface. And so what I will do, I will find the equivalent. That's all. The only story I'd like to tell is the following. These definitions are inside. So there are, I will send you the slides. There are a lot of examples about that, and you will see. I feel that I'm too deep in math. So here I will stop with the lecture because this lecture is more about all possible definitions and story like that. The only bit of information I would like that you will take from these pictures like this. Let's see. The key story here is that if I have different definitions, 1, 2, 3. All of them are logical. They are considering here from exposure. I have two vectors and I need to make a compromise. Then I will stop and then I will make another variation of U. So what will happen? What will happen is that here you will follow so this you can include all of possible perturbations, but still you will slide on tangential surface. Okay, you will be in tangential surface, so you will slide in the surface. What is clear from this picture? When you are dealing with sliding mode, never consider, please, the system in which the control is not linear, not affine system. Because if it will be affine, also of difference will come. This and this will convert to the people definition is the best possible. And unfortunately, it is not every time like that. And it is an example here. Then I've shown me, myself, and there are also experimental proofs in which it was maybe here. People made experiments. They considered nonlinear system with respect to the control, and they tried to realize what a relay controller with high storages and with saturation. And what happens? If you are making high storages, you are coming to one solution, and if you are considering saturation like that, you will go to the other solution. Question? So that is why be careful when control came into account the way of non-linearity. That's very important bit of information. So It is a strong story here. I think that some people left Holland. That's what I didn't like, because first of all, it was necessary to make introductory lecture, but I will do it tomorrow. So let's finish with that with definition. So bits of information you have to pick up. First, there are continuous functions, there are differential functions. Between them, there are lifts, maybe lifts you know. But there are still very important classes of functions which are not differentiable, but can be represented as an integral. Such functions we utilize. Second bit of information. Second bit of information is like that. Okay, you want or you don't, we need to go into the sets. Sets theory is not separable with the other story. So what you need to do, you need to do an important story. You need to define the solution newly. And what is important story? It's like in the family. It is compromise, but we need to follow what tangential surface. If you are starting in the surface and you will follow tangential direction, so you will keep there. And that was a remark of Filipov, which discovered it. And then there is engineering realization, which converted this story into what? Into simple algebraic equation. Because finally it is simple algebraic equation. And that was the step from math engineering. Why? Because we were able to find a control, if you know this. And if we don't, we are in trouble, because we have what we do. Okay? Let's see. Questions for this moment. So, I'm sorry if there is no question, why I'm lecturing. Say it, what you will tell me.
Example we have shown the limiter and the express what are the discontinuous.
Yes.
How you represent that second.
So you have non-linear systems. So that is why definition like that will be different than a definition like that. And if for the same system you will make different realization, you will have different answers. That is why take here every time consider system linear on control. Why? I will explain you why it's reasonable. Because in real systems, you have actuators. What are actuators? Electrical motor, hydraulic stories, like that. Or the students when I'm professor. But all professors are ladies, they wouldn't like to consider the behavior of their students individually. They are telling all of them are linear. So the same people are doing when they are considered actuators, like for example, electric CD motors, hydraulic storage, they are linear for professors. So because if not, you will go to the other stage. So if they are linear, so you have just output of actuator non-linear, but control is linear. So no problem in reality. But mathematically, there are problems, and that's what I'm showing.
Again, if they are non-linear, what?
If you were to have the system which contains a control non-linear,
Okay.
you will have different solutions. This is Filipov. And here you will vary control. And if control is non-linear, you will not have a line like that. You will have a curve like that.
Yeah.
And that will be different.
But is it multi-solution to be provided or only one solution?
Depends on your definition. So, both of Utkin and Filippo, they were searching for just one thing. The only I would like to finish is that maybe to give a final theorem about uniqueness. So, okay, let's scale the following. So, when you are considering such a system, what you need? You need that, of course, X is the vector of the state, U is the vector of controller, and V is the vector of perturbation. So, and you assume that all of them, U and V, are inclusions. So, and that's what happens here. You see? Here is the perturbation, here is the. So, that is why you need a theorem showing that differential improvement, that differential improvement or equation is right inside will have unique solutions. That's what you are asking about. This is the distance of solution. So what Professor Filipov told? He told the condition of existence for equation with the discontinuous writing part. What he told? He told that if the function is upper semi-continuous, what does it mean? This means that every time approaching to the point, you can go to the range.
Doctor, can you save your presentation on Flash? I will copy.
No, I think it is a standard, it is a standard. It is, yeah, do you have, no, don't worry. You have maybe one charger for standard, let's say, not Mac laptop. Do you have one?
No.
Is it USB-C, USB-C?
Yes,
USB-C,
Yes, C type.
C-type.
never had it. Okay,
You can save it and you can present from the screen.
Even a form chart.
okay.
I started in chattering problem in 81, and I'm still alive. Why? Because people are making something like motto. Let us make a chattering the God. Why? Because he will every time alive. So you cannot remove the chattering. The point that you can attend it. So what is the reason of the chattering? The reason of the chattering is infinite gain. Why? Because if you need to switch immediately, you need to have what? Infinite gain. So that is why. What is the reason for you to remove chattering? A reason is just to make the gain smaller. So if you, for example, will put continuous control instead of discontinuous one, you have less chattering, but you will not remove it. Why? Because you need to, for example, you need to put square root. Square root is good, but it still has infinite chattering. That is why you need to make Lipschitz control. Why? Because if control is Lipschitz, so the gain is finite. Okay, Lipschitz, because you have finite gain. I don't know if I'm clear. Yes, it is okay. So that is why let's say substitute discontinuous control with the Lipschitz one. Perfect. But if it will be still based on discontinuity, the second derivative will be discontinuous. So you can put a control as smooth as you want. A point is till which extent? That's what you asked me, or I'm wrong.
Yes.
So if you want to make your control smoother, please. But what I've told initially, I put it here an example of victims and two postmen. So if you beat your victim in each step, you are sure that what? That he will not go outside. If you wouldn't like to work too much, if you would like to beat him continuously, what you have to do? You have to know when the girlfriend of your victim is leaving. So why? Because you will wait there and tell, no guys, no way. Okay? But for that you need to know derivative. Is it clear? If you know when the uncle of the guy is leaving, it's the second derivative. So you need to, if you know that, okay, you can work less. I don't know if it is clear, this example. So to which extent you don't, so as weaker you make a controller, weaker should be perturbations. So you are unable to tell, I will have strong victim, but weak policy. Does it work? That's an answer or not?
Yes.
So I don't know, maybe it is.
There are costs. If we want to remove the shattering or reduce it, the gain will be reduced.
Yes.
Not be infinite to make the system respond faster.
Yes.
And reject the disturbance out of the
Yes, but the class of disturbances should be also corresponding, also weaker. That's the point. So weak victim, weak policy. Strong victim, stronger policy. You cannot tell that I have a strong victim, but very, very lazy policy. You know what will happen? I don't know if it is such example helps you to understand the story. Because I've tried to explain you how it goes, till which extent. So, to the weakness of it.
Yeah, understood.
Because you can extend, you can make weaker your control till the moment you will have big perturbation. If you will not have policemen strong enough, sorry, it is your problem, not mine. I don't know, maybe it's such a strange comparison, or it is good. Syed, what do you feel? So I don't know if I've answered your question, but
Yes.
so it works?
Yeah.
Okay.
What was the slide one? It's a right click and make it full.
Control F. Control F, make a full screen.
So such a way is better, much better, I think, if it will work. Okay. So the only I would like to tell that there is some restriction here to define the solution in Filipov sense. So this is a theorem of Filipov. He told, okay, the right-hand side should be not empty, for sure. Then it should be compact. What does it mean, compact? In the finite dimension means that it is bounded and closed, okay? You cannot have open set there. Because open set means that you can go to infinity. In the compact set, if it is closed, all is bounded. Then, convex, you know what convexity is. So, if it is not convex, why it's bad? Because what you can have there is that if you like to make convex closure, you can be there and it doesn't work. Okay? So this means that you should be non-empty, compact, and convex. So then the unique solution exists. It's like in standard differential equation theory. Even in the right-hand side, you can consider as a set. The solution is unique. That's very important. So, and moreover, he's shown that engineering idea does work. In which sense? Filipov told that if the third value, the right-hand side satisfies this solution, equivalence control exists. That's important. So what does it mean? This means that if you are following the surface, every time existing there's such a control signal which keeps you there. It is an important story. So that's, let's say, I will add maybe to my presentation my tea paper, my co-authors wouldn't like to include in the textbook because they told, engineering students, when they will see it, they will close the book. That is why the most downloaded chapter of our book is intuitive introduction. And that's what I will make you tomorrow. Intuitive introduction. Without that, it doesn't work because some professors left because they told us this guy is not about us. I'm about you. So let's start with the next perturbation, which is with the next story. So the other story is rate of convergence. So can you start please with another, with the other presentation? So this one. Modos de Lisantes 2 is in Spanish sliding mode 2. Okay. Good.
Control L.
Control L, that's another. Control L. Control L. It's not me. This guy died today. So here and here, and then control L.
I can see.
Here, here,
It's stuck. It's not like this picture.
oh, good.
This one. Yeah.
Okay. What people knows about sliding mode? What's the other characteristic of sliding mode control? So, return to the car. So, if I would like that the car will stop, what I'm doing? Brake. So, if my brake have only viscous friction, I will stop when? Never. Because I will converge what? Asymptotically. I will never stop. But I feel that cars are stopping. Why? Because dry friction is discontinuous function, isn't it? So we need to have the other type of convergence. Asymptotical convergence doesn't work for this model. Is it clear? That is why what I will speak as the next, rated stability. There are a lot of rates of stability, and cited knows that. Because he is writing the papers about predefined stability, isn't it? That's what I will speak about. That's also partly for you. Okay, guys.
Put that down. Okay, we change the caption.
So, and
It's not 12.
French,
That's not going to.
because it was working. Oops, it works. So it says battery. Okay, no connection.
You can use the wireless mouse.
Okay, let's see how it works. Okay, good. You know who is it? Lacuna. So that is why all American guys are angry because when I'm saying them that Russians, that control is Russian business because nothing without Lebanon. So, and you know the story that Kharkov, the place he wrote his Doctor of Science thesis, is Kharkov, and it was bombed in the first day of the war, and they destroyed at the university a monument to Lebanon. And I have a Lebanon medal, which gave me for my research. They gave me for my research. That is why I'm really angry for that story. It's my personal story. But what happens here? You see, he was searching about definition of stability, and he gave a stability definition. But the point is that what is the difference in our case? In our case, the difference is that we need to be stable not only with respect to initial condition, we need to be stable with respect to what? Operations is a big deal. So that is why we cannot speak only about stability of solution. We have to speak about stability of the set of solutions because there are many. Okay? That's another story. I will not pay too much attention to that, but you need to understand that what we are supposing standardly, we have an equation, and we would like to suppose that the right-hand side of equation has a solution, and its solution called equilibrium, isn't it? So what happens if we have a set? We have a lot of equilibriums. We have plenty of heads to kill. So that is why the only we have to suppose firstly that zero belongs to the right hand side. Okay? Then we will consider not only one solution with this initial condition, but the set of solutions. Okay. So, and here, for example, it is, say, do you know what is it? Which kind of algorithm I wrote here?
Maybe
Twisting. That was the first algorithm when I was young. Twisting. It twists. Okay, so how it works? Okay, where is the equilibrium point here? X2, isn't it? So now you have a car. So what happens with your car? If K1 is bigger than K2, what happens? You will be, this set should be winning because K1 is more than K2. And if K2 is more than K1, it is much more interesting. Why? Because if you will have zero here, in the right hand side, you will have every time zero. Why? Because you are searching for equilibrium, isn't it? So x2 for definition is zero, isn't it? Yes. So that is why here you will have a set for sure. If K2 will be more than K1, zero will be inside. If K1 will be more than K2, what happens? Any constant value will leave you out because this gain will be more than this one. And it will be constant. It could be not x2 equal x1 dot equal to 0. What does it mean? You have constant solution. Could be not zero. And it will be the same. So you don't have here equilibrium in that case. The only you have equilibrium is that when your brakes are stronger than the rest. So K2 should be more than modulus of K1. In this case, you will stop perfectly. I don't know if it is clear. What do you think, Said? Okay, that's the story. So, stability. That's one is searching for. What's the difference here? So, what stability means? Stability means that if you have some difference in initial conditions, you should be
Able to.
conversion
Able.
says to be in the maybe biggest vicinity of equilibrium. So what does it mean? For the any equilibrium, you have small set of initial condition. Starting with it, you will still be where? Inside of the vicinity. That's what will happen. So here, what's the difference? That it will be plenty of solutions, but with the same property. All of them will have the same property. Maybe epsilon for different solutions will be different, but for all of them, you will keep. That's the difference here at this point. Then the question is, what is uniform reduction stability? The point is that what you should have, you should have the property in which for any initial point, if your system is time dependent, the vicinity, the delta is dependent on T0. If it doesn't depend, if there is some delta which doesn't depend on the initial point, you will uniformly stay. That's classical definition. That's the same is for the sets. So here is very, very important story to understand what I'm telling you. What is but let's see. Instability means that you can, for some initial condition, leave every time. That's the usual story. So here, I like this example. It is very funny. This is typical railway system, isn't it? So what happens here? If I will forget about sine function. So double click.
On the screen.
On double tap.
Uh-huh.
I think you have changed something.
If we touch it, that's it.
It was not Hawaii.
No, it is touchscreen.
We double click on the screen.
That's one by one. So the point is that if the system does not depend on time, normally you don't have uniformity, because uniform is with respect to initial condition, initial time moment. Here, there is no time. Why I'm speaking about uniformity? Because there are plenty of solutions. I need to be stable uniformly with the set of solutions. That's the difference. So, and then if proposition Z is, if solution is stable, so and the solution is unique, so that's very important. I will tell you why. alpha is less than 1. Okay, what happens? You are starting here, and for any alpha, you will have different solution, okay? But for all of them, you will go to 0 in finite time. So what happens? When you are starting to be here at 0, the solution started to be unique. You have a lot of solutions, but at the moment you are in the equilibrium, just one. So that is why what we are searching for. We are searching for solution which works for every perturbation. What I'm telling here, if it is stable, it doesn't matter. Perturbations, if I fulfill the condition, always it's okay. So the solution, even if it is inclusion, becomes to be unique. That's an important point that it is not trivial to understand. So why? Because starting from here, I can tell that I'm unique. Can I return back? Can I know at this point which perturbation do I have? No, because I can start with one perturbation. I can start with the other one. I can start here with different solutions, with different initial condition, and I'll be here in finite time, so I cannot go back. It is not a standard group. You cannot go up. You cannot go to the future. You cannot reconstruct the future, the past. In that sense, it's not typical dynamical system. Why? Because normally in dynamical system, you can reconstruct, like for example in observers, you can reconstruct what happens in the system. Here not. But what is important that after you are kept, forget about perturbations. That's important. It is maybe new point for you. The other story is that, okay, we will speak about uniform stability, not too much. But what we will speak about is this system. It is standard system. If we will forget about sign, it will be x1 dot equal to x minus x2, and x2 equal to x1. So it is typical rotating system. Okay? So what you will have, you will have a set of cycles. But here, when you are putting sine function, what you have? A set of quadrats, you see? Because every time you will be one minus 1, minus 1, 1, and something like that. So you will make rotations. And to prove it, it's simple, like you are considering quadratic function. Here is the sum of modulus. It does not work every time like that, and I will speak about that maybe next lecture. So, and then you will have derivative, and it will becomes to 0 as you expected, is like it was in the standard quadratic function. When you will rotate in the cycle, here you will rotate in the square. So, then, someone told you will converge. To converge, we need the next step. What's the next step? Asymptotic convergence. Okay? Asymptotic convergence says where your solution is not only oscillating nearby, but it converges to zero. The same story is about set, and you see the difference. Now you are converting to zero. So, and that's an example I'm teaching for young people because they are searching for two things. First of all, let's say, what is asymptotic stability? Asymptotic stability from the first glance means that you will converge to zero. That's true. But there is a point which is very typical in normal life. What is important when you are searching for the good couple to live for all of your life? You need first stability and then attractivity, and not vice versa. If you will search that your partner will be rich enough, maybe it will be attractive, but it is unstable because he can become a bankrupt, no? So that is why you need to also stability. So that is why any definition of stability consists of 2 points. First, stability, asymptotic stability plus attractivity. You cannot have simple attractivity. That is classical example of the story when you are starting near to the equilibrium, but you are going outside and crossing 1 point, and then you are going to zero. So you lose attractivity. You get convergence, but you lose stability. So any stability is first stable and then attractivity. No, so that is why people prefer to.
What about the limit cycles? Does it have attractivity only?
Let's see. I'm speaking about equilibriums. I'm 100% agree with you in the sense that you see limit cycle is if you are constructing your control system basing on oscillation, it is much more robust than equilibrium point. Why? Because, for example, if you have simple linear system and you change the right-hand side, equilibrium point will be changed. If you have periodic solution and you have right-hand side, the form of periodic solution will be changed, but it will not disappear. Every time, periodic solution is much more robust than equilibrium point. Now the answer, please answer me your own question. You've told me till which point we need to suppress the chattering. Chattering what means? Means periodic solutions. They are much more robust than equilibrium point. I don't know if I've returned you your question. Or maybe you
oscillation, we cannot remove it.
Yes, we cannot remove it, but they are robust. You can make a lot of things, they will every time stable. But equilibrium will change and will be unstable.
But what about hardware?
So,
What about hardware with chattering?
so
Past updating.
stop. Return back to the policemen's. So you will tell that policemen's will not work too much for such a small salary, isn't it? That's what I'm telling you. You are telling me. So, or make a better policeman, or reduce your restriction about perturbations. Otherwise, it will not work.
Something has to be there.
Yes.
Something has to be there.
Yes, you cannot, but you see, even for example, how a lot of electrical devices are working. they are making something PWA. They are making the periodic solutions. It is only way to deal with, because otherwise you will be unable to do something. But periodic solutions are more strong. That's what I'm telling you. I don't know if you like that or not, but it is an answer. Okay?
Excuse me. Here you mentioned this system converges but not attractive, right? So it is not.
No, it is attractive, but not stable.
It's attractive and it converges.
It is attractive because you are starting here and you are converging here. But you going outside because it's 1 point. So if you will put vicinity here, you will be every time go outside. Because you need to cross 1 point. You need to make a loop around 1 point. Even your equilibrium was in the beginning. That's the point. So no stability here. It is attractive, but not stable. You know, sometimes you know such guys or such girls which are very attractive, but little bit unstable. That's more or less what I'm speaking about. That is why my lecture is for the young people, because they do need and make a decision. So, and it is the reason, let's say, let's tell truth. In many countries, people are searching for couples which has the same religion, same culture, because it's like a guarantee of stability. And then opportunity works. I don't know if it is strange or not for you to hear like that, but believe me that I'm trusting it. Even I'm married now with more than 25 years with a Christian woman. I'm not Christian, but that's true. That's how it works. I was born as a communist, so no any religion, nothing. So that's true. Okay? But I like your traditions. That's important. Okay, so then let's see. The bit of information I would like that you will catch is precisely that. That you need to follow, let's say, first stability, then attractivity. Then it could be different kind of attractivity, money, beauty, whatever. But first stability. Without stability, nothing more. So then different stability notion, that's a classical one. What does it mean? Exponential stability. So what does it mean? You see here the system. It is the system with discontinuous coefficient, isn't it? So we have a set of coefficients here which are changing from -1 to -3. Yeah? So because here you are changing from 1 to 3. Yeah? So and here what you are telling that your solution converges more fast than epsilon -4 and more slow than more fast than epsilon -1, but more slow than epsilon -4. That's what it's telling. This is -1 gain. Here is -4 gain. Okay. So you are oscillating in between. That's what happens. So, but it is still exponential convergence, even the system is representing like occlusion. So, then it is, let's say, -x in degree of alpha, where you are positive, and -x in degree of alpha, when you plus x in degree of alpha when you are negative. Why I'm putting that? Because you can not make the square root of negative number. That is why notation is like that. Okay? What happens here? If I have square root here, if I have square root, I have an integral, and an integral will be like that. Here we will have positive number. So and here, what will happen that I will converge in finite time. Why? Because this story will nullify when this term, which is negative for definition, will be equal to this one. Okay? This will be zero. So then we can find in t time in which we will converge. The same story for negative is. So, and this called homogeneous system, and homogeneous system will converge in finite time. That's mechanical example we were speaking about. And you see, this is a car stopping with what? What's that? Ratchet. So what we are doing, we are integrating the system twice, and we have the time of convergence more than derivative of initial condition for derivative. That's how it works. So, and this is a graph of position. You will see it converges in finite time in 2 seconds. So that is why. What is finite time convergence? Finite time convergence first is stability, okay? And then finite time attractivity. So what does it mean? This means that there exists an upper bound of the convergence time, which is upper bound of all solutions and for all initial conditions, you are reaching them. That's convergence time. So that's old school material. I mean, you see.
19.
Now, what we have discovered in 15, no, in 10, let's say, there are a lot of counterexamples and stuff like that. I don't have too much time to continue in the details. This is why I will go forward as much as fast as possible. So, we've done it right. You see, I was working in the end of, starting from 2005, about observers. We've made sliding mode observers, and our goal was, okay, to make sliding mode of finite time observer, and then to switch on control. So imagine that I would like to go to Mexico, and I don't have correct deeds where to fly. So what can be happened? First, I will go to Australia, then to return to Mexico if my observer will not converge fast. So what I need at least to tell that for any initial condition, I will be able to converge and then to switch on control. Okay? So that is why we were searching for such differentiators and observers which will converge in finite time. That's what we've done. So you see, this is a term belonging to conversion in finite time. But it is not enough because you need to escape from infinity from finite time. That's also important. So two things you have to fulfill. So what Khalil is telling, what normally people are doing when they would like that observer will converge fast. They are growing the game in order to accelerate convergence. So you have just one parameter to make two things. First, not to have a good convergence, but without augmentation of noise. If you will make a big gain, you will have a lot of noise. Here we've put it 2 years. Here it is a convergence and it is precision, it is here. And here it is how to escape from it. And you see here is all of the process of integration. That's how we are doing. So, and finally, what do we have? We have this integral, and we have this inequality. This means that for any initial condition, your convergence rate will be more than 2 arctangents. This means that you will converge less than pi, less than p. So the time of convergence here is less than p. That's fixed time convergence. It is mathematical property of the system, not of the control algorithm. Be careful. Here the difference started. Because fixed time convergence is good notion for math, but not for control. Why? Because you don't need, you cannot tell that you will converge in some point. You need to tell that you will converge before fixed time. You need to predefine it. And that's what people are doing. So this is the same example of the car. And here, what's the difference with the previous formula? There is no initial condition here. All depends on the system parameters. And you can estimate upper bound of the time. So, and here you see, this is a typical breaking story, but you will converge before 0.8, even for very big initial condition. You see? That's a big fixed time convergence. And we've made it, and then my student Andrei Polyakov called it fixed time because we called it uniform. But he published just one paper without too much content, and that is why finally we published the paper together about notion of you need for sliding mode. It is 2014. And maybe I will send it to you also because it's all math behind it. So now controllers. Fixed time convergence is we are estimating through Lyapunov function is not too good, but it is always a way. The method needs to verify stability, but the problem is that there is no numerical method, and the controllers are not too good for realization. Why? Because it is a bad story. Imagine that you'd like to converge from any initial condition to the fixed time. What you will do? You need infinitesimally strong actuator. Do you have it? No. So such kind of controller doesn't work in practice for nothing. It is just mathematical story. So, but nevertheless, there is a predefined time of control. Not convergence, predefined time controller, but convergence is still a fixed time. What's the difference? The difference is that in controller you have what? Parameters. And if you have parameters, you can adjust them. adjusting parameter, you can have a predefined time. That's what's the difference between fixed time. Fixed time is mathematical property of the system. Predefined time is not only fixed time. You need to select what? Parameters. That's the difference. And so then you can select the parameters, and then you can put different stories. So, and here I would like to show that you have two gears. You can make this faster or this faster. If you make this faster, you will have overshot. If you will make this parameter faster, you will lose the precision because you will make bigger gain. So that's or one or another one. So you need to go to the beauty or to the richness. Okay. And now, what is on the model? Maybe I will show you with on the board. Here you see, here you are keeping precision. So up. No, it's good. Prescribed time. Prescribed time. Prescribed time. So, prescribed time stability, what does it mean? How it works? It's very simple. It was using a lot of functions, maybe more in the rockets technique, when you need interception. What does it mean, interception? You can be in the correct place in the correct time. Precisely the time, not before and not after. So, what does it mean? No, it's even worse. So, imagine that you have linear systems. It is alpha minus alpha x. So, richer is alpha, faster is the surface, is the convergence. Okay? So now it will be never finished because it is exponential convergence. So what I need to do? I need to do infinite gain, no chance. That's like a chattering you are speaking about. So what I will do? I will tell, okay, I would like to be at 0 in time td. Let's say, what I will do? I will integrate so then I will tell that so what I will tell, I will leave out the now. So what I will tell that in this time it doesn't matter what initial condition did I have, I will have 0. That's all. That's prescribed time. So good. Would you like to work with such a gain? No, for sure. It goes to infinity. Why it works in the rockets? You see, interception problem, and mostly how the anti-air Earth-to-air rocket was working. It was exploiting near to the airplane. So the gain is still not infinite. If you've seen, for example, the airplane destroyed by Russians over Ukraine, it was a very big process in Netherlands. They've shown the rest of the airplane. It was full of holes because they've exploited the rocket around 10-15 meters between the airplane, and it was with very small balls. It's like a shrapnel, I don't know if you know this word. A lot of big, small balls with a big kinetic energy. They've destroyed it. So that is why you are not going till infinity. And that was the reason. Why it works? Because you don't need to continue. So if you beat the airplane, so the work is done. So the airplane is there. So does it work for sliding mode? Not, because the sliding mode is life after death. In which sense? You need to stop the car, even there are perturbations. So and you need to continue stopping. So that is why this story, prescribed time, doesn't work. Philippe's definition doesn't work here because it becomes to be not compact set. Even this control at all is bounded. That's another story, that's another proof. But Philippe's definition doesn't work because the set is already not compact. That's what I'd like to tell, and I've seen that cited waked up. So this means, let's give me a couple of words. So, 4 bits of information. When you are dealing with the sets, 1 bit. First, stability, then attractivity. That is why my recommendation, look a girl for the same culture. It is kind of stability. Because, so second, let's say attractivity, up to you guys. You can choose whatever you want. You can choose asymptotic, you can choose exponential, you can choose fixed time, and when you have a control, you can make predefined and prescribed. Prescribed, you know exactly the time, but I don't know how you will continue. Predefined is not exact estimation, but you can have upper bound. And it is very difficult to realize it. For controller, it's impossible because you need a model in all of the space. All of the model are in some compact. If it is in compact, why do you need fixed time? No, because you are in finite set. Predefined controller, you don't need if you are in finite set because fixed time requires less force. That's the point. So don't ask me to speak too much, please, because I will never finish. Thank you so much.
If you have a question, you can later on still.
I hope that, let's say, and I'm thoroughly asking you to send the invitation to students and professors which left because they thought that I'm a mathematician. I am, but I cannot continue without them. And tomorrow I will make much more popular lecture. No math, just jokes. Thank you.